Potentiometric magnetism, the Hall effect. Have you ever seen a brushless motor spin smoothly or watched a tachometer count gear teeth? That is the Hall effect in action. When electric current flows through a thin piece of material and a magnetic field passes through it at a right angle, the moving charges get nudged to one side. That sideways nudge builds a tiny on-Hall voltage across the thickness of the material. The stronger the current, the stronger the magnetic field, and the thinner the material, the bigger the measurable voltage. Flip the magnet or the current direction, and the Hall voltage flips sign. Words for the geometry, how to aim things. Think 3 directions. Current flows along the strip, magnetic field points through the strip, and the Hall voltage appears across the strip. If any 2 of those flip, your reading changes sign. Useful for finding north versus or south, pole or direction of rotation. Types of Hall sensors. Linear Hall sensor, analog. Outputs a voltage that rises and falls with field strength. Many are potentiometric, meaning mid-supply with no field, higher with north, lower with south. Hall switch, digital. Inside the chip is a linear Hall plate, plus an amplifier and a but comparator, with hysteresis. On at one level, off at a slightly different level. Great for simple on-off speed or position sensing. Bipolar versus unipolar. Hall switches. Bipolar toe. Needs north to turn on and south to turn off. Unipolar. Can turn on and off with the same pole as the magnet moves away and back. 3-wire package. Power, ground, and mount signal. Often an on, open collector, organ open drain. You pull up with a resistor. Some industrial versions feed a 4 to 20 milliamp transmitter for long runs. Classic applications. Gear tooth speed sensing. A magnet plus a Hall switch watches the teeth go by and produces crisp pulses. Perfect for tachometer and totalizer inputs. Brushless direct current motors. 3 Hall sensors read rotor magnets and tell the drive which coils to energize. Smooth, efficient motion with no brushes. Proximity and limit sensing. A small magnet on a machine part trips a Hall switch with an adjustable air gap. Non-contact current sensing. A Hall sensor near a conductor or inside a magnetic core measures the field created by current. Handy for high current or isolated measurements. Selection and installation. Quick checklist. Magnet matters. Pick a stable magnet grade and shape. Align, north-south, so the field crosses the sensor at a right angle. Set the air gap. Too large and the field is weak. Too small and the parts may collide. Start with the datasheet's target gap and adjust. Route the wires. Use twisted pair for the signal and keep away from motor cables. Add a pull-up resistor if the output is open collector. Shielding and mounting. Mount firmly so vibration does not modulate the gap. Avoid large steel masses that can shunt the magnetic field. Temperature drift. Magnet strength and sensor offset both vary with temperature. Choose parts with the right temperature rating for the job. Troubleshooting. No pulses at all. Check wiring. Power, ground pull-up. Verify magnet polarity. Reduce air gap. And confirm the gear or target is actually moving past the active face. Wrong direction or count. You may be reading the wrong pole or wrong edge. Flip the magnet or rotate the sensor to match the datasheet orientation. Weak or jittery signal. Excessive air gap. Loose mount or steel nearby. Tighten hardware, shim the magnet, or move to a cleaner location. Electrical noise. Long unshielded leads near drives. Add man-gun shielding. Twisted pair, and Debounce, or ging filter, in the controller. History nugget. In 1879, Edwin Hall discovered the effect while still a student. It lived in physics labs for decades, then integrated circuits. Turned it into cheap, rugged sensors that now run motors, speed pickups, and current probes. Everywhere. Wrap up what to remember. Hall sensors turn magnetic fields into voltages. Flip the magnet and the voltage flips. Choose linear for measurement. Switch for clean on-off pulses. Set air gap and orientation carefully. Mount solidly, route wires cleanly, and expect temperature effects. Huge thanks to Tony Coupault and the open source community for the instructional models behind Crash Course Instrumentation. If this helped, please like the video, subscribe to Crash Course Instrumentation,